Hello. Think I'm live? But here's another random live stream. Round 2. I had a live stream this morning and it didn't go too well. A lot of technical difficulties this morning. Hopefully this time this time it'll be different, hopefully. Something went wrong with my capture card. I have no idea. It's been a whole week like that. Now I've gone simple. For some reason the capture card doesn't play nice with OBS, so right now I'm just having a window capture. What is it called? A window capture scene set up in OBS, so it just captures the scene that is driven by the capture card. I hope this is not freezing, but I think it is actually. I'm trying to move the screen. Okay, so there's just a delay. Okay, good. Not freezing up. I can march on. I had a lot of stuff planned, so I really wanted this to work because I'm going to be busy in the next few days and I might not have a chance to get this out. For all of you that are new again, this is a live stream series I'm trying out. Each live stream session is meant to be short, hopefully short and working. I'll be discussing a new topic every session. So far I've covered a lot of math topics, a lot of matrix topics, a lot of VEX math matrix topics. And hopefully I can expand on this further and get into more advanced and interesting topics in the future. Hey, Flaming Burrito, nice that you made it. And Q Gel Blitz. I think I got that right. I'm not sure. So the live streams are meant to go on live to the public for a limited amount of time, like 24 hours, before I take them off and make them perk members only. This is my way of trying to produce more content while trying to encourage more engagement. Things are really tough these days, and I want to cover more. And like, I've always done beginner videos. No offense, I'm getting a little tired of beginner videos. I want to move on to something more exciting, more advanced than Houdini. But that takes time to prepare and learn and stuff. So this way, these live streams give me the opportunity to explore more advanced topics. But anyways, this live stream, this particular one, is mainly on concept, and we're gonna explore more on how these matrix, these transformational matrix and rotational matrix, and how they work. How do they look like? Sure, I can plug this in and make this guy rotate. And this is a matrix. This is one of the topics we covered in the last few sessions. You make a rotational matrix. Let me put that 90 back in. So this is a rotational matrix, which is different from the transform matrix or translation matrix, which I had shown in previous sessions, where I had the sine f here and then a cos f here, f here, and this just moves it in a circle. Why is it different? Because this is a translate. So this here, it is filling up the translation parameters here, and the rotation are 0, 0, 0. So this is not a rotational matrix. And today we're going to explore what exactly is the difference and how does that matrix look like. And to help me with that, I actually created some little Python apps. So because the matrix are really long to write out, and I don't want to spend the whole time writing it out, this guy, right? So I created a few Python apps to help me. And these Python apps are going to be available to the Perk members. And the live stream, this live stream, is going to be public forever. Just to make things simple. Just to give something to everyone, so everyone has something every single session without overloading myself. Now, what I wanted to show you, let's go back to this guy. This is the 90 degrees. Oh, let's put that 90 back in. Now, this is creating a rotational matrix. It's actually a transform matrix. It does both rotation and translation all in one. So that's the beauty of matrix, that you can fit so much data in it and then just run a single matrix operation. And we talked about this before. A lot of computers, like I think it was the PlayStation 2 and PlayStation 3, when they first came out, they specialized in matrix math, matrix multiplication, which made it super fast. So that's all they can do. As long as you can cram in as much information in the matrix, every operation, every matrix operation runs the same CPU cycles. And that's like their chip design. That's the architecture that they have. I'm not going to get too deep into that. Just remember that when you're running matrix operations, it's much more beneficial to the CPU, to the PC. So this is creating a 90 rotation on the Z, which is causing this rubber toy to tilt to the left. It rotates to the left. Now this, we feed in the Z rotation in this rotation vector, which eventually gets into this maketransform, which creates that transform matrix that does both rotation and translation. But what does it look like? So I'm going to feed in this is a little app that I made in Python. It is, you just fill in the same amount of information, except this one you need to tell it is a 4x4. And then the translate, it's the same thing. So it's the filling in the T in here and then filling in the R over here. So let's put the 90 and then generate matrix. I just want to see how this matrix looks like. The only bad thing about this is that it's so tiny. I don't know if you can even make this out. So that's one thing I need to improve on this app, is that to make this larger so people can see it. Oh, I know. I can copy this to a notepad. That's a good idea. Because there's no point if you can't see this. And I can increase the font. Okay, too big. Bear with me, bear with me. Let's go a little bit bigger. Okay, I think that's good. That's really good. So by putting that, let's cover that one up. So 0, 0, 0 translation, 0, 0, 90-degree rotation on the Z creates this matrix. Unfortunately, it puts all these dots in there, which is really annoying because it makes it harder to read. I really hate. Another thing to improve on the app. This little Python app was created very quickly. Okay, there, that's nice and clean. What I want you to see is there's like the first column, the second column, the third column, and the fourth column. The fourth column is usually reserved for translation. So this is where this is the part. Oh, let me see if I can. There we go. This is the part that does the rotation. And we can see, oh, actually, okay. I should give it a 0, 0, 0 first, so you can then generate this. So you'll know that this is what it usually looks like before the rotation. So you can see a before and after. Oh, how should I do this? Open another notepad. Okay. So this is the one here. Now, the one on the left has no rotation. The one on the right has rotation. The only difference is this guy over here. Let me highlight it. Only difference is this -1. Everything else should be the same. Let me... Oh, and this here. Okay. This here does the rotation. So 1, 1, 1, 1. So you can see the diagonals 1, 1, 1 all the way down. This is called an identity matrix. It's sort of like multiplying 1. It does nothing. It just gives you exactly what you, the input. So the negative, rotation on the z-axis by 90-degree angle gives you this rotational matrix. This is the part that does the rotating. What is it? And I said this part, I said that part does the translation. So what we can do, like translate 1 and then generate matrix. Oh, 90 here. 1. Copy this. Boom. Oh, right. Those. Man, I've got to get rid of those decimal points. Okay. Now the difference is that this is now 1. So this is the x. This is the translate to x over there. Scooch it over on the x-axis. And everything else is the same except for, and this is the rotation, as I've showed. So this is actually code. This is actually spitting out VEX code. So we can actually take this. Okay. And I'm going to put it into a Wrangle. So we're going to take in, let me drop down a new Wrangle. So this is creating that matrix at P, and we're going to actually multiply it. And we should get the same thing. Let's see, that is there, but it's rotating on the opposite side. Let me see if I put a negative here. Okay. So it was just getting confused with the negative. I might have a bug in the Python script. But hopefully this gives you an idea. I'm trying to bring up the matrix. Wrong one. Hopefully this gives you an idea of what the matrix looks like when you do the translate and rotation, and how you can use it in a Wrangle to apply it to your objects. But how is this more convenient than using a transform node? Because it's definitely not that simple or intuitive. So why would you ever use this? Well, one thing, it's in a Wrangle, so it gives you it opens a lot of possibilities. And another thing is this rotates on the spot. So it rotates. It rotates while keeping the orientation. So you can see that this rubber toy faces is actually tilted, as opposed if we used transform nodes. And we did it the way that I had it before, like the sine or cosine, this way. This is actually just rotating the position, but not rotating the orientation. So he's always upright. If you ever wanted to rotate him around on the spot, that's where the Wrangle would come in handy. Now, what I'm going to try. I'm going to show one more example. Let's see. Let's come over here so it's a little neater. What I'm going to do is I'm going to move him up. Now let's grab this Wrangle over here so I don't have to type it all over again. Now he's rotating. He's rotated on the tilted, but what happens if I move him up before applying the matrix? Oh, come on. Okay, I'll just put 2 here. Okay, so here I've moved them up. Move up. Okay. And then here it's just rotating around the z-axis, which is not, because the origin's right here, so he's not really rotating on the spot, is what I want to show you. If I ignore this, he jumps back to the origin. This is moving, this has moved it upwards. So what I would, if he rotates on the spot, what I would expect it to do is rotate like in the center. Like I would expect them to rotate like this. This is what I would expect. Oh, there we go. But instead he's over here instead. So let me template this. Let me switch this. Remember, the origin's over here. Ish. Yeah, somewhere around here. So how do we actually do this rotation? Like rotate him in the center, pivoting on the center with transformational. Oh no. Oh no. This was happening this morning. I can't. Oh, this is not happening, is it? It is. Okay, good. Sorry. The known system gets locked at times. I have no idea why. But anyway, it's working now. This thing was locked. That's what happened. I couldn't right click. I couldn't pan on the node network, which drives me crazy because I pan like crazy. So this is rotating on the center of his belly, pivoting on the belly. This is rotating on the origin. From here to from here, and I move him up and then rotate it over there. So that's not what we want. How do we do the rotation from center position using wrangles and transformational transform matrix? Well, what we can do is we know that this okay, before let's remove that first. So this is where he starts off. Let's remove that first. This is where he is, and we know the origin's over here. All we have to do is rotate him back to the origin because we know this works on the origin position. If I ignore this and put this back in, this works. This works properly when he's at the origin. So all we have to do is add an offset to bring him back to the origin, apply the matrix, and then reapply the offset. I know it sounds like a lot, but once you implement it in the wrangle, it's actually not that bad. So again, before we apply the matrix, you can ignore this line over here. This line is just for debugging. I'm outputting the matrix to see how it works. So while I was implementing the Python script. Let me hide that. Oh. Okay, there. So you don't see it. Okay, let's take this. And what we're trying to do is move him back to the origin before we apply this transform matrix. So let's get the center first. Let's get the center. Let's get box. So this will give us the center of this object. And what I'm going to do is I'm going to move him let's see, how do I say this? The center position of this object already tells us the offset, how far he's moved away from the origin. Okay. So that, oh. Okay, so that is that's the up vector that we have to offset. And that's how far the center has moved away from the origin. This is already an offset distance that we can use. So all we have to do is at P, subtract it, is what I'm saying. This will move him back to the origin. And then now he's at the origin, well, this matrix should work fine, as we've seen before. Let's apply it. Let me get rid of those overlays. And it works nicely. But we still want him back up there, right? So all we have to do is just reapply this offset. but not minus. It's a plus now. It would be the opposite. And then this would give us a nice rotation on the spot. So let's test this. Let's give it a different rotation. Instead of rotating on the Z, let's give it rotating on the Y. This seems like it's working. 10. Your screen flickered for a second. Oh, sorry. I was switching between the other monitor trying to grab one of the apps. Let's see. What else did I want to show you? Now, if you ever wondered what if you manipulated the matrix, if you get attached to this function and you only want to use this type of function, like you're really attached to this rotation XYZ, which is called Euler, so you know, this is like the Euler rotations, and this is like the rotational matrix. Later on, this gets into a little bit more advanced with gimbal locks and Euler rotations and rotational matrix and quaternions. Like, it gets messy. But for now, just know that this is actually two different ways in calculating the orientation, in calculating how to rotate the object. It's two different ways. And in the future, when you get into gimbal lock, you'll know that it actually sometimes will give you a different result depending on which way you use. Do you ever use the rotate function when working with rotational matrices? Let's see. I don't remember. This one. Oh, sometimes. Not a lot. Not a lot. We can actually try this. This looks fun. Amount. I'm not sure. Let's see. You have rotate. Vector axes. This is fun in that you can pick the axes. So you can... I've only shown you very simple examples, but say if the axes was something really, really weird, like... let's give this a long line. And I'm gonna transform. Sorry. I see the comments. Give me 1 second. Point. You have something like weird. Say you want the rubber toy to rotate on this axis. Like around this thing, twirl around this guy. Instead of the perpendicular XYZ 90 degrees. That's the simple version. And I think that's where this function will be very, very useful, because you can calculate the axes. Or let's see, can you? Or am I just making stuff up? Through rotates, angle must be given radians, and XYZ is the rotation order. XYZ is the rotation order. What is the axis? Axes must be normalized. Yeah, okay, so the axis is definitely it should be the direction, is the rotation direction. So this is really handy, because you can feed this into the Wrangle, calculate the XYZ vector, calculate the vector of this line, put it into this rotate. So that's very handy. It's just a little it gets a little complex when you're figuring out this vector line, which is actually not that bad, because it will be, because this starts at the 0, this is the origin, so the vector would just be the position of the second point, which is I don't know if you can see that. Let's see. Let's make this bigger. Text large. Well, that's not very large. It's this 1 here, so it's just the position of the 1, really. That is the vector line. Let's see if we can do that. 0.1, because I'm grabbing this input, the second input, and it's 0 based, just to confuse everyone. And then name and point number. Name, I want the position. Point number, well, that's 1 because I see it right on the viewport right here. So say this is my vector line. This is, I don't know, direction, I'll call it. Rotate. Now we're going to rotate our M. I'm going to create a blank. This should result in an identity matrix. Actually, this is a good time for me to test that out with one of the apps. So if I wanted a identity matrix, what would that look like? 1, 1, 1. Yeah. So 0, 0, 0 in the translate, 0, 0, 0 in the rotate equals an identity matrix. I know you can't see that. I closed all my notepads. Okay. So this is the identity matrix. That's what I want here. Let me actually label this identity matrix. There we go. Take this, and we're not going to, let's see, rotate. If I apply this, it won't do anything because it's the identity matrix. And what we're going to do is use the rotate, and it requires a matrix. So we're just going to put an M, amount, and the axes. M amount, let's say 45. I wonder if this is in radians though. Radians. What was the last one? I have the memory of a goldfish. Oh, right, direction. The axes. Rotate M. I think you need, it's asking, it's throwing an error because, oops, trying to get the tooltip up. It's asking for a reference to the matrix. So I believe you have to put like an ampersand or not. How do I get the reference? In C, it usually would just be an ampersand. Oh, sorry. I have the wrong name. Okay, that works. So VEX is based on C. In C++, I got used to doing, like, when they ask for this ampersand, it's passed by reference, and you have to dereference it, and then a whole lot of stuff. But I guess in VEX, you don't have to worry about that, because this just seems to work. Or not. Oh, because I have this here. No, let's make this go away. Take this out. Take that out. Oh, right. We have to apply it. All I did was rotate the identity matrix, but I didn't do anything with it. Void. Okay. So let's go here and put it here because this line applies the rotational matrix to our object. So let's rotate it and then apply it. And I did something really bad. It has skewed it. Now, one thing why I was outputting this was to debug stuff like this. I will get onto the comments. Just give me 1 second. I just have to update this because it was using M. I'm going to use identity. And all I was doing was cheating to go into the details. It's coming in here and inspecting this, but this is really hard to read. So this is what inspired those these little Python apps that I created. I think it's matrix. Here, matrix 2. No. I made 3 apps in total. Okay, so this should be a 4x4 matrix because it says right here 4x4. So I would just put 4x4. Copy this because I don't want to read this. This is like very hard to read. Copy this, and then it would put it in a nice matrix format so I can see this clearly, but you can't see it because it's too small. And I'll just paste it in here. So this, I mean, it still looks messy, but it's way cleaner than reading this. So we can see that this is practically 0, 0, 0. Well, this is 5 degrees. 5, 1. That's practically 0. So it's shifting mostly on the z-axis. But the shearing, I'm not sure where the shearing comes from. Let me look at the comments first. Is there an advantage to using maketransform? Oh, maketransform is in the Wrangle, so it'll open up possibilities in the future where we want to make more complex things. Right on top of my head, I'm trying to think of like the first thing that comes to mind is vector fields. So if you're doing like a pyro sim or a flip fluid sim or particle sim and you wanted to rotate, you wanted to create a vector field that will tell it to rotate on the spot, like move to your left, pivot on your spot, but not on the origin, like how I showed you here, how it was pivoting from the origin when you apply it. And that's what's going to happen when you're using the transform node. If we go here, he moved up. And where's my transform? I'm going to reuse this guy. This is actually rotating. So it's no longer rotating around the pivot, like where it started, because he started over here. Or even if you want to say like, okay, but that's the translate. Let's actually do something in the rotation. I don't know, 45 here. This is still pivoting from the origin because this is his position. So he's moved. His position is moved. But if you look at my translate here, I don't have anything here. Like this is 0, 0, 0. All I have is 45 degrees and I really just want him to tilt. So that's one of the advantages. In here, if you really wanted to rotate on the spot using the transform node, you'll have to fidget with this pivot. So you'll have to like, just like the Wrangle, how we figured out we had to like get the center and then reapply it, like do that offset. This, you also have to tell it the pivot. You also have to do something similar. But I can't use a transform node in the .NET if I'm doing field vectors. If I want to build a vector field to influence my simulation, the best way would be to use Wrangle. I actually don't know if you can use transform nodes to build a velocity field or a vector field. Oh, right, back to the rotation. So hopefully that answers your question. I went on a little side trail. The rotate. It's doing shearing. Let's see, where's my line? Line here, shearing there. Oh, it's shearing on the line. Oh, that's pretty cool. So if we actually, so does that mean if I manipulate this line, it'll change? Ooh. Oh, because I didn't normalize this. Oh, right. Okay, yeah. Now it's back to the good scale. So what I just did there, if I can, you can see that line. So there's a line right here. That was the original position. So he's tilted with the line. I think so. Should be tilted with the line. It's hard to tell. He's so far apart. Let's remove the move. Let's take that out because I can't see. So I believe he's tilted with the line. I think so. But the line is affecting how the direction that he's tilted. And the reason why I got rid of the shearing was because I normalized our directional vector, our directional line. That's this guy. That's this white line here. Normalizing a vector means that a vector contains two sets of information. It has the scalar information and it has the directional information. What that means is that, well, you know what the direction is. It's like if you have a finger and you're pointing somewhere, that's your direction. That's your vector. The scalar is the magnitude. It's how long that finger is. So the length of that finger, if it's too long, it affects this rotate because you're rotating it unevenly. The x-axis might get a larger rotation than the z-axis, and what it does in the end results in this shearing because of the unevenness. By normalizing it, what we say is I only care about the direction of this vector. I only care of where that finger is pointing. I don't care how long that finger is. But that's what normalizing means. It makes the vector of length unit 1. Mathematically, that's what it's doing. And if it's length unit 1, well, it's just 1 unit. It doesn't have any weight. It's just weight of 1. Hopefully that makes sense. Okay, so this was meant to be a short stream. It went a little longer than I thought. Try to stay tuned. Ooh. This is the stuff. So I was adding notes for this project file to be released for the perk members because that's what I do. So this is the stuff that we've talked about in the previous sessions. That's a little sneak peek. In the upcoming streams, I want to show you the gears. So I'm making this little gear thing, the rotational matrix. This is perfect for gears. Now, right now I only have 2 gears, but I'm going to add a bit more to it. So this is exciting. This is one to demonstrate what you can do with it. No, you're not distracting me. Well, it's better than talking to myself. No worries. So, yeah. So I'll just cut it right here. Cut it as short as I can right here, and I'll see you in the next random stream time.